Good evening, class. Tonight I would like to talk about chemical equilibrium and chemical thermodynamics. Suppose a hypothetical reaction A mole of compound A plus B mole of compound B will produce C moles of compound C, and this reaction is in equilibrium. Therefore, you have two arrows, the forward arrow and the reverse arrow. For this type of reaction in equilibrium, the equilibrium constant expression would look like this. You have the concentration of compound C raised to its coefficient, or moles of compound C, all over concentration of compound A raised to its coefficient, multiplied by the concentration of the compound B raised to its coefficient. Looking at the equilibrium constant expression, we could see that it is just a ratio of your product and reactants. Knowing that it's only a ratio of your product and reactants, we could interpret KEQ values or equilibrium constant values accordingly. If the value of equilibrium constant is equal to 1, it essentially means that there is an equal formation of product and reactants at the same time. Or the rate of the formation of the product is also equal to the rate of the formation of your reactants from your product. If the value of your equilibrium constant is greater than 1, it necessarily means that the formation of your product is more favored. On the other hand, if the value of your equilibrium constant is less than 1, it means that the product is unstable and therefore the formation of your reactant from the product is more favored. This concept is related to spontaneity of reactions. When we say spontaneity of reaction, we are referring to Gibbs free energy, or the change in the Gibbs free energy of your reaction species. First and foremost, let us define what the word spontaneous means. Spontaneous means that it follows its natural course. A spontaneous process, for example, the falling of the water from atop your waterfall down to its base, is a spontaneous process. On the other hand, a non-spontaneous process is when the water from the base of your waterfall goes back to its top position. In reaction thermodynamics, we describe the spontaneity of reaction in terms of Gibbs free energy. A negative change in Gibbs free energy means that a reaction goes from a higher energy state to a lower energy state, meaning the products are more stable than your reactants. On the other hand, a change in Gibbs free energy, or a positive change in Gibbs free energy, means that your reactant goes from a low energy state to a high energy state. It means that the products are more unstable than your reactants. Now, how is it related to our equilibrium constant expression? Gibbs free energy and equilibrium constant are related using this equation. Delta G is equal to negative RT ln of KEQ. The natural logarithm of your equilibrium constant value multiplied by the gas constant and the temperature at Kelvin is equal to change in the Gibbs free energy. So this necessarily means that a KEQ of 10 will yield to an ln of KEQ value of 1. Therefore, it results to a negative delta G, or negative change in Gibbs free energy. On the other hand, a KEQ value of 0.01 results to an ln of KEQ, or natural logarithm of KEQ value of negative 2, and therefore it results to a delta G, or Gibbs free energy change, that is positive. We could write that relationship as If the value of your equilibrium constant is equal to 1, the delta G is 0, meaning the reaction is in equilibrium. On the other hand, if the value of your equilibrium constant is greater than 1, it results to a delta G of negative, which means that your reaction is spontaneous or it proceeds as is. And finally, if the value of your equilibrium constant is less than 1, it results to a positive change in Gibbs free energy, which means that the reaction is non-spontaneous. When we talk about reaction thermodynamics, two terms that significantly affects the spontaneity of your reaction or your delta G are the terms delta H and delta S. Delta H means change in enthalpy and delta S means change in entropy. What does a negative change in enthalpy mean? A negative delta H means that the reaction is exothermic. When we say exothermic, it releases heat. Apart from being an exothermic reaction, it also means that your products have more stable bonds. On the other hand, a positive delta H means that the reaction is endothermic or it absorbs heat and it results to the formation of products that have more reactive or less stable bonds. Let me give you an example to this. The electrophilic addition of hydrobromic to ethene results in the formation of alkyl halide. This reaction has a negative delta H. Remember that a negative delta H means that the reaction is exothermic and the products have more stable or less reactive and stronger bonds. Looking at the reactants, we could see right away that we have very reactive species here. This one is a very strong acid and this one is a very good nucleophile. This one is a strong acid and good electrophile at the same time. You could see right away that the reactants are more reactive than your product due to its chemical reactivity or the Brownstein and Lewis acidity and basicity of your reactants. On the other hand, the product has more stable and less reactive bonds. Even though the carbon here is partially positive, it is not that positive compared to this hydrogen, which easily reacted with your ethene molecule. Now, what does a positive change in entropy mean? A positive change in entropy means that your products have more disorder, and a negative change in entropy means that your products have less disorder. In the given reaction, we could see right away in the product side that we only have one molecule. And in the reactant side, we have two molecules. So in the given example, the change in entropy is positive because a two molecule system is more disordered than a one molecule system. Looking at the reaction given, the Gibbs free energy or the change in the Gibbs free energy of the reaction is negative. The values of your delta H, delta S, and delta G are experimentally determined. But still, we could surmise by looking at the reaction or the reaction mechanism. We could surmise the sign of delta H, delta G, and delta S, whether or not they are positive or negative, just by looking at the chemical reaction or by looking at the reaction mechanism. So in the given example, our delta G is negative. And as I've said before, the spontaneity of reaction is affected by the change in entropy and change in enthalpy. And that is represented by this equation. Delta G is equal to delta H minus T delta S. So what values of delta H and delta S would result to a positive or negative delta G? Looking at the previous equation, the equation is delta G is equal to delta H minus T delta S. A negative value of your delta H and a positive value of your delta S would result to a negative value of your delta G, meaning an exothermic reaction which results to a more disordered products would necessarily be a spontaneous reaction. So why is it that a positive change in disorder or a change in entropy is more favorable? There is a saying that goes, the universe is geared to a state of greater disorder. Even in chemical reactions, that is also the case. Molecules want to achieve a state of stability and greater disorder. So delta H of negative is exothermic, more disorder, and spontaneous. If we have a value of negative delta H and negative delta S, the value of delta G could either be negative or positive. It depends to the value of your delta H and delta S. If the product of your temperature and the change in entropy is greater than your change in enthalpy, the reaction would essentially be non-spontaneous. So it is spontaneous when delta H is greater than T delta S. And it is non-spontaneous when delta H is less than T delta S. So how about when we have an endothermic reaction which produces greater disordered products? We could have either negative delta G or positive delta G. We could have a negative delta G value if delta H is less than T delta S, and we could have a positive value if delta H is greater than T delta S. And finally, if we have a positive delta H and negative delta S, it is essentially a positive delta G, meaning the reaction is non-spontaneous. In the previous reaction that I have given, electrophilic addition to alkene, our thermodynamic values are, we have a negative delta H, a positive delta S, and a negative delta G, meaning this reaction is exothermic, results to less disorder, and we have a spontaneous reaction. So in this context, our T delta S is less than delta H, which resulted to a negative delta G. In the given example, or in the given reaction, the reaction mechanism looks like this. We have a partially positive hydrogen and partially negative bromine, and we have a nucleophilic carbon double bond carbon. So this pi electron is being donated to this hydrogen. This bond is broken to produce a reaction intermediate called carbocation. So this hydrogen is bonded in your ethene, and the formal charge of this carbon becomes positive. In the background, we have your bromide ion, which was released from your hydrogen and bromine bond. And since your carbocation is a good electrophile and your bromide ion is also a nucleophile, then it will react with your carbocation to form the final product, which is this product. Take note that this carbocation is called a reaction intermediate, meaning it is only a transient species that occur during your reaction. Chemical reactions are represented by a Gibbs free energy diagram. So what is a Gibbs free energy diagram? A Gibbs free energy diagram shows the energy level or the energy state of your reactants, intermediates, and products during the course of your reaction. So the x-axis of your Gibbs free energy diagram is reaction coordinate or time. And the y-axis of your Gibbs free energy diagram is, it represents the energy of your system. Take note that your reactants in this context we have more energetic reactants and less energetic products. So the Gibbs free energy diagram looks like this. So in here we have your reactants, and in here you have your products. So for example, if this one is 200 kilocalories and this one is 100 kilocalories, the change in your Gibbs free energy is a negative value. Your delta G is negative. Take note that a lower energy state means that your product is more stable. So in this context, your reactant is less stable than your products. But in order to jumpstart the reaction, we have to supply a certain amount of energy. You have to supply this one until, for example, this one is 600 kilocalories. So this amount of energy is what we call the activation energy. Activation energy is the energy that is required to start a chemical reaction, because two reactants would not immediately react unless they supply the activation energy, or unless they overcome the energy barrier for a reaction to occur. Okay, so take note that after achieving your activation energy, it goes to a minima or a minimum value. So this minimum value is a metastable state, which is your intermediate. A reaction intermediate is a metastable state, and what we mean by metastable state is that it is temporarily stable, and thus it is just a transient species that occur or that is formed during the reaction. After the formation of your reaction intermediate, it goes to another maxima or maximum value, and finally producing your products. So if we look at the reaction mechanism, we have your reactants here on this side, and the nucleophilic attack of your reactant resulted after supplying the activation energy. So this nucleophilic attack signifies this point, and after the nucleophilic attack, we have the formation of our intermediate, which is a carbocation intermediate. And this state signifies this point. And finally, the nucleophilic attack of your bromide in the background signifies this maximum value. The formation of your product results in overall lowering of your energy state, and finally results to a negative change in Gibbs free energy. Therefore, this reaction is stable and spontaneous. So prior to ending our topic, let's interpret some Gibbs free energy diagrams. By the way, since we have an intermediate in this reaction, we could say that the mode of reaction is stepwise and not concerted. So in this type of Gibbs free energy diagram, we have reactants here and product here. This type of Gibbs free energy diagram, we could say that the reaction is spontaneous, meaning delta G is negative, and that the reaction is concerted. Okay, so why is it concerted? It's concerted because it has no intermediate. On the other hand, this type of Gibbs free energy diagram, in which your reactants have lower energy state than your products, is what we call a non-spontaneous reaction, because your delta G is positive, and here your delta G is negative. Okay, so apart from being a non-spontaneous process, this reaction is also a concerted reaction, or the mode of reaction is concerted. Okay, so looking at the energy state of your reactant and product, we could see right away that the delta G is negative here, meaning this reaction is spontaneous. But take note that we have formation of intermediate here. So the mode of this reaction is stepwise. On the other hand, we have this type of reaction in which your product has a higher energy state than your reactants. So this reaction is delta G is positive, meaning non-spontaneous reaction. And since we have an intermediate here, it is also stepwise. Let me give you another hypothetical Gibbs free energy diagram. This hypothetical Gibbs free energy diagram is obviously spontaneous because the change in Gibbs free energy is negative. And it is also stepwise because you have two intermediates, this and this. But how many steps does this reaction have? So this reaction have 1, 2, 3. So it has 3 steps. When looking at the Gibbs free energy diagram, the minima, or these blue regions, represent your intermediates, and the maxima, the lowest minimum state, is your product anyway, and the maxima, or your maximum points in the chemical reaction, represents the steps in your chemical reaction. So these steps could either be nucleophilic or electrophilic attack, and basically they are just acid-base interactions. So this marks the end of our lesson. Before concluding our lesson for tonight, I would like to give a brief summary. The equilibrium constant expression is just the ratio of the concentration of your products and reactants. Basically, a value of 1 means that there's an equal formation of your product and reactants, or equal rate of formation of your product and reactants. A KEQ value that is greater than 1 means that the formation of product is more favored, and a value of negative 1 means that the formation of your reactant is more favored. Furthermore, the measure of the spontaneity of a reaction is your Gibbs free energy, or change in Gibbs free energy. A negative change in Gibbs free energy means that your reaction is spontaneous, and a positive change in Gibbs free energy means that your reaction is non-spontaneous. So when is a reaction spontaneous? It is when we have a KEQ value of greater than 1, and non-spontaneous when the KEQ value is less than 1. This relationship is represented by the equation delta G is equal to negative RT ln of KEQ. Finally, we have the thermodynamic values delta H, or change in enthalpy, negative and positive. So a negative change in enthalpy means that your reaction is exothermic. It releases the heat from the system and thereby results to the formation of a more stable product. And we have endothermic reaction, which means that the reaction absorbs heat from the surroundings and results to the formation of less stable products. We also have delta S, which is your change in entropy. A positive delta S means that there is more disorder in the system after the product formation. So at least in thermodynamic application, it means that a positive delta S means that there is more disorder in the system after the reaction, and a negative delta S means that there is less disorder in the system after the reaction. An exothermic process is favorable to have a negative delta G, or spontaneous reaction. So if you have negative delta H, most often than not, the reaction is also spontaneous. And furthermore, if you have formation of more disordered system after your reaction, it essentially means that the reaction is most often spontaneous as well. Finally, we talk about Gibbs free energy diagram, which maps out the change in energy level or energy states of the species of your reaction during the course of your reaction. So a Gibbs free energy diagram shows the energy state, or the energy of the system, plotted with time, or reaction coordinate. We have, for example, this type of Gibbs free energy diagram shows the reactants at 0 seconds and products at this particular time. So the energy state of your reactant is higher than the energy state of your product, meaning your products are more stable than your reactants. And this lower energy state results to a negative change in Gibbs free energy. Another thing to remember about Gibbs free energy diagram is that to jumpstart a reaction, we need to supply a certain amount of energy to the system, and that is what we call the activation energy. In this type of Gibbs free energy diagram, we also have the formation of a metastable state, which is called the intermediate. And finally, this type of reaction has two steps, 1, 2. So all in all, we could say that this type of Gibbs free energy diagram shows a spontaneous reaction. The mode of the reaction is stepwise. It has 2 steps and 1 intermediate.